the presenter will present his presentation named by using of genetic algorithms to find the optimal location and sizing of a static VAR compensator to minimize the real power losses. I will leave the talk to Mr. Mohammed Jannat, and I hope from him he will just take 10 minutes for his presentation and 5 minutes for Q&A. I hope we will start now. Thank you so much.
Use this or do you want me to?
It's up to you. Thank you. Thank you very much. في بوينت لا ما فيش. بسم الله الرحمن الرحيم. أولا السلام عليكم ورحمة الله تعالى وبركاته. I will start to present my papers. Using genetic algorithms to find the optimal locations and the sizing of static VAR compensation to minimize real power losses. Static VAR compensators provide fast-acting dynamic active compensator for voltage support and reduce system losses and so on. Multi-objective optimization problems involves a number of objective functions which are to be either minimized or maximized. Non-dominated sorted genetic algorithm 2 is used for the search of optimal solution. Our work uses NSGA2 in searching for solution consisting of both the static VAR compensation location and size that minimize both the reactive power losses and the installed reactive power of static VAR compensation. We are talking about two objective functions. Okay, here we can speak about optimization method. The problem is modeled as by criteria optimization problem, minimization of real power losses, and here we can see the equation to compute the real power losses. The second objective function is minimization of reactive power compensation, and we can see the equation. Our operational constraints, power flow balance equations, and power flow limits and bus voltages. Our results, NSGA has been applied in actual 28 bus medium voltage distribution network that supplies several villages and Banat region in Serbia Republic. Objective function 1 is the value of static VAR compensation. Objective function 2 is the value of power losses. The calculation were done for the two cases with one static VAR compensation or two static VAR devices. Single line diagram for the network that we applied our solutions for. We can see it's a radial system and consists of 28 buses. Okay, with one static VAR device, here we can see a table that we have a set of 20 optimal solutions. Final solution choice can be made based on value of compensation or value of power losses, or we can use another thing as a comparison between the costs of compensation and power losses. From the table, we can see if the compensation more than 1.6 megavar, then it will be located at bus 19. Now, if we draw the two objective functions together. Sorry, there's an error because it's one static bar device, not two static bar composition device. By drawing all pairs of objective functions for all optimal solutions, we can see the need clearly between two states number 14 and 18 here. We can see here the need between number 14 and number 18. With two static var devices, we have also 20 optimal solutions. We can see from the table compensation, if the value of the compensation less than 0.49 megavar, it will be located at bus 21. If the compensation more than 3.1 megavar, it will be located at buses 10 and 19. With two static var devices, by drawing all the pairs objective functions for all optimal solutions, the knee point is between the two states, 14 and 18. Sorry. Here we have a comparison between the two cases for one static var device or two static var composition devices. We can see clearly here there's no difference between the two sites or one site for the small values of compensation. But the two cases indicated that in the small sizes less than 0.49 megavar must be only in the bus 20 and 21. والله مرت فيها مرتين مش تمشي. اوكي خليها تزيد خليها. اوكي شو الشاشه؟ شو الشاشه اوكي. هذا ايش تبغى صار؟ As we say before, a comparison can be between the cost of static var composition, the amount cost of the static var composition, and the power losses, and for a period. Here we suggest three situations for 10 years, for 20 years, for 23 years. We can see the curve for the cost of the power losses by line, blue line, and the red is for the cost of the static var composition. All the solutions above the line, the blue line, they are not economic solutions. So we can choose one of the solutions. I think number 14. Solution of number 14 can be the best solution, static var composition value located at bus 19. The value is 22.44 megavar. Power losses, it will be 17.30 megawatt hour. If we have another comparison in 20 years, we can see that all the values under all the solution under the blue line, most of them, I think 18 solutions under the blue line. That means all the solutions under just solution number 20 and 19, they are not economic, but all of them, all the other solutions are economic. And if we choose according to this comparison, we can choose number 18, solution number 18. Okay, the static vacuum value will be 3.8 megabar. For the 23 years, we can see all the optimal solutions are under the blue line. That means all of them are economic, and we can the solution state number 20 is the best solution. Our conclusion: an application of NSGA 2 was presented for finding the best location of static bar composition. The searching is for solution consisting of both the static bar composition location and static bar size that minimize active power losses. Multi-objective algorithm has been applied on real 28 bus network to obtain the set of optimal solutions for one location and two locations. There is a good reduction in total power losses for each total static bar size. Some comparisons were done also to choose the best optimal solution for one location was done by applying costs. Thank you for your attention.
Nice presentation. Actually, now we can start our pictures. We have only 5 minutes. We hope we can get 3 pictures maximum. So we'll start. Phase 1 phase 1 of the 2. Phase 1.
You can ask me in Arabic إذا كان اللغة الإنجليزية مش متاحة ممكن تسأل حتى بالعربية.
Yes, I have a question. I go back to slide 11. The study the power and the safety cost, total power cost.
بيشرح حقيقة. Okay.
So you elaborate more on this figure. Why the cost of states.
We have in okay. We have 20 solutions for 1 until 20. Just remember with me, we have 20 solutions. Here in this picture, in this figure, we have for all solutions. If we start from number 1, the cost. This is the cost of installing the solution number 1. Solution number 1 is to install 0.16 here to objective function 1, 0.16 megavar. The same for the losses. If we remember 20 megawatt hour. This is the cost of 20 megawatt hour for 10 years. For 10 years, we speak now about 10 years. If we compare, it's economical for solution number 1, but usually for multi-objective optimization, there is not only just one factor. Maybe you can choose another factors to in another way. There is more than one factor affect your choice to take this optimal solution or this or this. But all 20 solutions are optimal. Okay, you're welcome.
Any more questions? Can I have one more question? This is one of
You're welcome to.
presentation صعبة شيء موجودة صعبة موجودة presentation comparison of several artificial neural networks approaches.
Firstly, I will talk about introduction to the paper, including machine condition monitoring and motivation of the study. Second, background. A third, experimental setup. Then the result and discussion, and finally conclusion. If we definition the condition monitoring is the processes of monitoring some particular condition in the machine, such as vibration, temperature, or any parameter, and any change in this parameter will indicate error in the machine. In our paper, we focused on the rotating of the state of rotating machine, especially three-phase induction motor, by measuring the vibration. And with development in MEMS technology, we can fix at any MEMS in the rotating bar to record and store this is vibration signal that's used for monitoring the three-phase induction motor. And this is the motivation of the study. The popular questions are why condition monitoring and what its importance, how work, and what the problem that solves it, and what the solution for this problem. If we use condition monitoring, we can improve the machine efficiency and reduce the maintenance cost and avoid breakdown. How? By monitor and analysis any effect parameter in the machine, like the vibration in the rotating machine. If we use conventional accelerometer for measure this acceleration signal, this accelerometer have many disadvantages like cost, large size, need external power source, need cable for external power source. And for solve this problem, we use the MEMS accelerometer instead of it. Now, if we talk about the MEMS technology, this technology is used to produce any integrated devices like sensors that mix between electrical and mechanical components. All these devices have many advantages like small size, low cost, and low power consumption. Our accelerometer has another name called variable capacitance accelerometer based on the operation principle. As shown, the structure of MEMS have two fixed plates and one movable plate is suspended between them and air gap between them. When the acceleration is applied, the movable plates will move and the capacitance C1, C2 will change, and this change will be proportional to the acceleration value. Thus, the change in displacement will change in capacitance. The case specification of our accelerometer output data sampling rate up to 3600 Hz, measurement range sensitivity have just 4 values, 2, 4, 8, and 16J, resolution up to 13 bits, and the operating temperature range between -40 to 85 Celsius degree. If we move to the experimental setup, this slide shows our test rig. As shown, the MEMS accelerometer were fixed on the outer body for 3-phase induction motor. Data processing, and finally, the decision making. First, in data acquisition, we take the reading into 2 cases, healthy case and an unhealthy case, imbalance case, and all cases take in different loops. The work of signal processing completely in frequency domain because the vibration signal in time domain is very complicated. هيكون our work بتاعنا completely في frequency domain. This is the first result. The upper graph represents the acceleration signal in time domain, and it's very complicated. The lower graph, it's a spectrum. In a healthy case, and full speed, and 90% load. The upper graph presents low power spectrum for the acceleration signal, and the lower graph presents high frequency spectrum for same signal. The blue signal represents in healthy case, and the red signal in unhealthy case. We know that the amplitude of the acceleration signal in an unhealthy case is always greater than a healthy case, and we can use this method for monitoring the three-phase induction motor. As shown in a graph, the x-axis represents different cases of loads, and the y-axis represents the magnitude of the acceleration signal. The blue curve represents a healthy case and the red unhealthy case. Firstly, in fundamental frequency, secondly in the first harmonic, and thirdly in the second harmonic. We can note that the magnitude of the acceleration signal is always greater in healthy case. For this reason, we can use this method for monitoring the three-phase induction motor. From our experimental results, we can reduce the conclusion of our paper into 4 points. We can use the MEMS accelerometer for condition the monitoring and state the three-phase induction motor. And the amplitude of the acceleration signal is always increased when volatile condition. And we can use this method for low-cost condition monitoring for the rotating machine. Thank you for attention and any question.
Thank you very much for a nice presentation. Please.
حددتي؟ اللي يحدث في الروتيتنج ماشين في الاندكشن هن الاعطال متنوعه، لكن العطل اللي احنا اشتغلنا عليه اللي هو الانبالانس كونديشن، لكن في اعطال يعني كثيره تحدث في الروتيتنج ماشين. لا AC induction motor. DC generator, yes. ليش DC generator كالوت؟ هو هذا كان متوفر اساسا في يعني القسم، يس ما كانش عندنا اختيارات. عفوا، شكرا.
نعطوا طريقه مرتين ممكن يكونوا بعض الاوفرز زي يكونوا خارجيه شو كانت في حد منهم اونلاين والله السيشن في حد
اشوف بس ساره ممكن موجوده اونلاين. يمكن موجوده اونلاين.
السلام عليكم سارة، هل تسمع فيها؟
Yes.
باي تمام. هل البرزنتيشن موجود عندك؟ هل بدي شير يور سكرين؟
لا ما أعتقد.
alright. البرزنتيشن رقم 53 هذا صح؟ هل
أيوة صحيح.
باين عندك؟ فيديو صح؟
فيديو أيوة.
اوكي. الفيديو بالصوت بتاعه او انت تبي تشرحي شخصيا؟
بالصوت الفيديو.
اوكي تمام 100%. في الحالة هذا هنا حنشغل الفيديو. هل تشوف فيه على الشاشة حاليا؟
لا ما طالع عندي.
اوكي شوي بس. شير سكرين.
Hello everybody, I'm Sarah Sobhi, graduate student in the College of Computer Science and Engineering at the University of Jeddah. On behalf of my team, I'm blessed to present to you our work entitled Comparison of Several Artificial Neural Network Approaches for Fault Classification in Power Transmission Lines. Through this presentation, I'll provide an overview of power distribution system protection and the reasons why we choose to use artificial neural networks. Afterward, I will describe the proposed schema and how artificial neural network models are created. Following that, we will discuss the results of this study. Finally, a conclusion will be provided. For years, humans relied on power distribution systems to transfer the energy from production areas to consumption areas. System analysis and protection were the major issue in controlling these networks. The main challenge is to design a reliable and low-cost systems to ensure the minimum amount of fault existence. The solutions vary from relying on human operators, model-based methods, signal-based techniques, and artificial intelligence approaches. Nowadays, the reliance on human operators to deal with the faulty situation decreased, as many efforts have been made to protect the power distribution system from any interruption. Besides, automation process control has proven its superiority over human operator due to its ability to handle and control large systems while respecting time constraints. One of the most common artificial intelligence model is artificial neural network, which modeled after the human brain. These neural networks are designed to recognize a pattern by learning. Each neural network consists of nodes with input values known as neurons, connected by some links known as connections. Every connection has a weight, which represents the importance of the variable. The value of each neuron in the hidden layer is calculated by some sort of formula and passed to the next layer. Then an activation function, which is a mathematical equation, will be used to determine if the receiving value should be activated or not to provide the final output. Artificial neural network was chosen because of its multi-layered structure, which allowed parallel processing, making it able to handle a large amount of data and solve non-linear problems. Also, it's fault tolerant since it can deal with missing or corrupted data. For this study, we chose to work with three common artificial neural network architectures, which are backpropagation neural network, radial basis function neural network, and probabilistic neural network. since several studies have focused on power distribution system analysis and fault detection using various artificial neural network architectures, but only a few have compared the best performance between multiple architectures, especially among those three. Thus, we focus on these three models to analyze their performance and accuracy and to compare them with each other to identify the most effective one. Let's take a closer look at those approaches. The backpropagation neural network has the ability to propagate backward from the output layer to the input layer to calculate the gradient of the loss function and readjust the weights for each layer. While the radial basis function neural network uses the radial basis function that given by this equation as an activation function. In probabilistic neural network, the pattern layer with hidden nodes for each training instance determine how close the input vector is to the training vector. In terms of time consuming and computational cost, the previous studies show that the backpropagation neural network is a slow algorithm and computationally cost, while radial basis function is known for its fast training ability, but it tends to be costly to evaluate with large datasets. Also, probabilistic neural network is fast and costly computationally. In terms of suitability with large system, backpropagation neural network and radial basis function tend to be not suitable for larger systems, while there were not enough resources talked about probabilistic neural network and complex systems. Moving to the methodology that we followed during this study, we started with data acquisition from a power system model that was simulated to generate the dataset. Then we performed some data pre-processing where the dataset was labeled with the corresponding class and the data feature were extracted. After that, the artificial neural network model creation, where fault classification was performed using the three artificial neural network architectures. And finally, the performance for each artificial neural network was estimated and evaluated. So this slide showed the model that we used to generate the dataset. This network represents the hydrophobics electrical transmission system, and since we focused on the three-phase fault in transmission lines, a three-phase fault block was programmed at the MTL7 bus, as shown with the red box. So in order to get various samples of data for each fault type, a variety of parameters were used as listed in this table. After the simulation, the three-phase current and voltage signal were obtained from the model. The total number of samples was 1188 samples. Each row of the dataset was labeled with the corresponding fault type, and the mean value of the current and voltage signal were calculated, and the final dataset includes 6 input values and 11 target classes. Finally, the input data were normalized between 0 and 1 to avoid taking too much time during the training process. After that, we created all networks by following these steps. We prepared the input values, which are the three-phase mean voltage and current. Then it went through many calculations in the hidden layer using the corresponding training function. Then it moved to the next layer to apply the proper activation function based on what artificial neural network we use, and deliver the final output, which is a dummy value that represents each fault type, like this one here represents the BG fault. Let's have a look at this table, which represents ANN specifications and results. So for the input layer, there is 6 input neurons for each model. For the hidden neurons, there are 35 neurons for both backpropagation neural network and radial basis function neural network chosen experimentally, and 832 for probabilistic neural network selected automatically based on the size of the training space. All the models provide an output with 11 neurons. For data partition, we allocated randomly 70% of the data for training, 50% for the validation and 50% for the testing, except for the probabilistic neural network. It doesn't contain a validation step, so the remaining 30% were allocated for the testing. We used PatternNet for both propagation neural network and radial basis function as a design method, and NeoBNN for probabilistic neural network, then the corresponding training and activation function used. And finally, the result showed that the backpropagation neural network finished in 21 seconds with good percentage of accuracy rate, equal 97.3%, while radial basis function provide a high classification accuracy of 99.3%. However, it takes longer than the other two models with 52 seconds. Probabilistic neural network dominates over the other two models by giving the highest accuracy of 99.4 in 16 seconds. And here you can see the confusion matrix of each model. In the end, we found that all three models assured that the artificial neural networks fit perfectly in power system classification problems, which will make these systems more reliable and robust. However, the probabilistic neural network model has the highest accuracy with the shortest prediction time. Also, we found that the performance of the artificial neural network affected by the data preprocessing and normalization, the network architecture, the training function, and the data division process. Thank you so much for your attention, and feel free to ask any question you may have.
If you don't mind, please could you give us a short CV? We didn't prepare anything about the university. Please give us one before if you don't mind.
Hello, Sarah, are you there?
Yes, I'm there.
The professor asked a question. He's going to repeat it now, okay?
Okay.
Hello, Sarah.
Yes.
Hello, Sarah. Yeah, good morning. First of all, I would like to apologize me and on behalf of session chair committee for the delay which out of hands. And first of all, we'd like to, if you don't mind, to give us a short CV, just 1 minute, okay? You just introduce yourself, please. Thank you.
I'm Sarah Subhi. I'm a graduate student at the University of Jeddah. I get my bachelor degree from King Abdulaziz University in computer science.
Okay, thank you, Sarah. Let's start our questions, please. If you have any question for the audience, please, if you have any questions. أي سؤال لو سمحتوا بالعربي حتى نقدر نترجمه مش مشكلة. في أي سؤال لو سمحتوا؟ دكتور في أي سؤال؟ لجنة.
Yes, I saw that you used 70%.
Sorry.
Hello, Sarah.
Yes.
Yes, I saw that you used 70% of the data for training and 15% for validation and 15% for like testing, right?
Yes.
But I didn't see you mention the number of data sets. How many, how large the data is, how many data sets you used?
The dataset contain 1188 samples. 1188.
1188. So like 1,000 data sets?
Yes. Yes.
And how variant like these data, what types of faults and the location of fault and whether it's isolated or not isolated fault? How various?
Okay.
Yeah.
There
Could you
is
explain that?
11 fault types, 3 phase fault types, and if you can see the slide number 9, we vary from a table. We have a table of parameters that contain 11 fault type and fault resistance.
اوكي. في اي سؤال حضور؟
Thanks, Sarah. Thanks so much for the nice presentation, actually for the valuable presentation. Thank you so much and have a nice day. Bye-bye. لو ما فيش سؤال ننتقل للرابع والأخير. عفوا. اولا احب نرحب بالاستاذ او بالدكتور اسف عز الدين درسي. نحن سعيدين بحضورك اليوم معنا، الدكتور عبد الحميد، الدكتور عبد القادر، الدكتور عبد السلام. شكرا لحضورك الكريم، بارك الله فيك. اوكي، عندنا النكست برزنتر حيكون مش عارف هو اونلاين ولا؟
انا قاعد بحث اونلاين في
ما فيش
بيبل في عايشه
عبد العاطي القناعي comparison. عبد العاطي مش قاعد أنا؟
I don't think so. Hello there. هل عبد العاطي موجود داخل المستمعين؟ إذا كان عبد العاطي يقدر يدز لنا رسالة على الشات. I don't think so. I don't think so. لا مش موجود. حتى presentation مش هنا.
نقفل السيشن نحن.
نقفل السيشن بعد في سيشن أخرى. نفتحها. هي تبدأ بعد هذه. Artificial intelligence. لكن تبغى تفتحها تو.
خلاص ما نحن نقفل السيشن بتاعنا باش نعطوا السيشن موجودين. Okay, I would like to thank all participants here. Thanks so much for your coming. Actually, unfortunately, Mr. Abdulati is not presented today. Thank you so much and have a nice day for all. Bye-bye. شكرا جزيلا لكم. طبعا احنا المفروض في شخص رابع يعطي ولكن للاسف لم يحضر، فحبينا نشكر جميع الحضور الكرام اليوم على حضوركم وجميع من قدموا العرض من دكاتره او من طلبه او من ماجستير. نشكرهم جزيل الشكر على ابحاثهم القيمه.